other bias circuits. This is now your emitter stabilized bias circuits under RE model. So this time, we have a resistor at your emitter terminal. You have to change this into an EC equivalent model, and you have to plot your current flow. You have IS and IB, you have IO, IO prime, and IC, as well as I, then IE. So this is your voltage at the base, at the same time where we can get your impedance at the base. Voltage input, where we have our impedance I and impedance IN. We have also the output impedance. So we have first to get your input impedance. But before, we have to get the equation of your voltage at the base so that we can get the impedance at the base. So that is beta REIB plus RE times IE. At the emitter, we have this current for your IE equals to IB plus beta IB plus I. And your I, that is a current that will flow at your RO, it is from BO going to your BE. So we have BO minus BE over RO. And BO is equals to negative RL times IO. Remember the polarity of your BO, that is positive and negative, but the flow of your IO is against the polarity of your BO. So that's why it is negative RL times IO. And IO is equals to RC all over RC plus RL times IO prime. And we have to substitute that one to your BO. So therefore, BO is equal to negative RL in parallel with RC. Then BE is RE times IE. So at the collector, using KCL, we have IO prime is equals to beta IB, which is your IC, plus I. Then substituting the value of your I, which is BO, minus BE over RO, to your equation of your IO prime, and combining all IO prime to your left side. So we have your equation of your IO prime. And beta IB plus I equals to IO, so therefore we can have your IE equation as IB plus IO prime. Then we have to substitute this IO prime to your equation of your IE, which is IB plus IO prime. Then combining all IE to your left side. Then we have the equation of your IE in terms of IB. So therefore, for the voltage at the base, it is beta REIB plus REIE, substituting the equation of your IE in terms of IB, and dividing your equation voltage at the base by the current IB. So therefore, we have your impedance at the base. Getting the parallel of RB with your impedance at the base, that is impedance I. And adding your RS to your impedance I, that is your impedance IN. For the output impedance, you have to set BS to 0. So that is equivalent to RS in parallel with RB plus beta RA in parallel with RE plus RO in parallel with RC in parallel with RL. Then for the voltage gain, which is BO over BS. BO is equals to negative RL times IO, and we know IO already. So therefore, substituting this equation to your IO, we have first your IO prime. So we have now your equation of your IO. It is in terms of IB and IE. Then we have already derived the equation of your IE in the previous slide. You have to substitute that one to your IO equation. Then your IO equation is in terms of IB. Substituting this one to your BO, so we have now BO is equals to negative RL times RC over RC plus RL and times your equation of your IO. So this is now your equation of your BO. Since voltage gain, that is equals to BO over BI, where BI is equivalent to your voltage at the base. So we have first to get the least common denominator of your voltage at the base. So B over BI, that will be our voltage gain. Since our input is BS, so we have BO over BS. So we have to get the equation of your BI over BS, that is equals to impedance I over impedance I plus RS. Or we can rewrite your voltage gain as EBS times impedance EB times impedance I over impedance IN. So that is our EBS. For the current gain, it is I over IS. So we have your IO equals to negative B over RL, and BS equals to impedance IN times IS. So therefore IS is BS over impedance IN. Substituting that one to your EIS. So we have negative B over BS times impedance I over RL. So BO over BS, that is EBS. So we have your EIS equals to negative EBS times impedance IN over RL. So that's all for emitter stabilized bias circuit.